Okay, so this is a docking experiment that I just proposed. I'm very excited to be here to present my talk. My group is interested in interactions between short-motif peptides and proteins, and we're trying to model them, and by developing protocols that work when we try to understand what characterizes these types of fascinating interactions. So first of all, I want to present my group. I really like my people. These are people that basically interact together to study interactions of proteins, and what I'm going to talk about is mostly work about these four persons on the upper part and the point is not working. Yeah. Okay, so I want to talk about peptide protein interactions in a way that we talk about the modern way of communication, which is for young people mostly mediated by SMS, which is not short message service but short motive sequences. I think that many of the really important interactions work with these short motifs that are very interesting because they can be easily manipulated by the context. So it's really important to have a common context, and if you have a common context, you can communicate with very short messages. And if you want to change the context, you can achieve very good information. And that's what the cell basically does. And as Ben said, and others, many of the interactions are maybe unstructured regions that include all of these motifs. So we are trying to model this. I'm going to describe shortly protocols that we have developed over the years. And what I'm really excited to talk about is the two new protocols that we developed in the last 2 years. The last one of AlphaFold this year. I'm going to maybe talk about AlphaFold protocol because I just don't have time to describe the other things. Okay, so the basic protocol that we developed was to it's called the Rosetta Textbook. It's part of the Rosetta framework, which basically uses, simply said, Monte Carlo sampling in an efficient and smart way to sample and identify the information. And the idea here was to optimize and to challenge, to address the challenge of flexibility during the docking process. While if you are docking, you have two different rigid bodies, to optimize this is pretty simple. In the case of peptide-protein interactions, the peptide changes. The peptide doesn't have the structure before. And that's considered a challenge. We solve this problem by using a combination of iterative optimization of rigid bodies and internal optimization of the peptide within a force field that slowly but surely adds the passive potential, so that at the beginning we start with a fraction and then we end up with tightly packed structures. And if you want to do this in a more extended way, you can also do folding of the peptide within the binding site, and that just takes much more time, but it works too. And so this was very good, and it actually led the field forwards. It has led to the development of many additional protocols which can each and everyone teach us something about these types of interactions. That's a really good thing. One of the examples that I want to show here is the example we have done in the last year. Is trying to see how post-translation modifications can change the binding of a peptide, or in this case, the binding of the immunoproteome. So together with a group of Fatmer at the Weizmann Institute, we discovered and mapped using proteomics many new types of peptide-protein interactions that lead to the immune system activation, MHC binding. We modeled the different interactions, the different modifications that basically allow us to explain how changes in post-translation modifications change the ability of peptides to raise the immune response by binding to specifically that they couldn't find before. And that is actually also a framework that we are using now for machine learning to adapt our protocols also to residues that are not sampled or optimized when we solve structures for real-time learning. So the problem with these protocols was for a long time that we couldn't really extend them to global docking. So if you don't know where the peptide binds, these protocols contact you need some initial information. And what we have done in the last few years is we have solved this problem by thinking about conceptually how these interactions are actually formed. And that's what I want to talk about today. So we thought about peptide docking in a way that we say that there has been a study about 10 years ago by a group of Serrano that basically showed that the structures of peptide protein interactions look actually like monomer structures. So it's not that it's something very new centered, and we also have looked at many salt structures, experimental salt structures. We saw that the basic patterns that characterize interactions also occur at peptide protein interactions, and also in many cases these peptide protein interactions really look like a complementation of the protein monomer. So if we change our conceptual viewing of how peptides contact the proteins and look at them rather as like a patch or part of the monomer, we can actually extend our ways of how we model interactions to include protocols that we developed for monomer modeling and not necessarily for docking. And that has worked very well. So I'm going to show you today 3 different ways of how to do this. One of them, the first one, is one that was published quite a few years ago, that looks at the interaction from the peptide viewpoint. So in that protocol, we were talking about features that we saw over and over again, and which is described in the L database, linear motifs. In many cases, when we look at protein-protein interactions that are maybe defined as unstructured, we can find sequences that are conserved. And these sequences basically should, in principle, correspond to some structural motif. That's what we think. And so if they correspond to a structural motif, then it could well be that in this energy landscape that we see here, the bound conformation has a much lower energy. Maybe this common structural motif that has a better energy in the interaction, maybe this structural motif could also be available in the ensemble of the peptides before we bind. So the idea here is that it's not that this peptide will have a defined conformation because of bind. We all know, we don't see this not in any other experiments and not in other experiments. Most of the cases, the peptides don't have a regular structure. But if we think about it in terms of concepts, that we have an ensemble of conformations, and there might be a few of those that adapt this conformation, but because there are too few, we can't see them in experiment, we might still be able to use this as a bias to actually guide our modeling. And so the idea is that if these conformations occur in the free energy landscape, maybe we could use this as a modeling structure. So we could basically decouple the conformation in the freedom of the peptide from the conformation freedom of the rigid optimization. And this is basically what we are also doing in Rosetta in general. The initial modeling protocol of Rosetta, the original one was to reduce the space, the sample space, by looking at local preferences to these fragments, and then optimizing these fragments as a combination to a global conformation. So we're doing something very similar. We are using this fragment library to describe an example of peptides, and then we just dock them with physical docking and refine with our Rosetta experiment. And that works actually really well. And this doesn't work, but the protocol works. Okay, so this is to show how well this works. So we have here a plot that shows on the x-axis the distance from the correct structure, and on the y-axis how many models, how many complexes in the benchmark are modeled within this cutoff. So what we show here is that within 2 angstrom cutoff of RST, which is pretty near, we get about 35% of the complexes modeled well with this protocol. This is it. And so, okay. So this is comparison to other methods. You can see that this protocol works much better than the rest, or similarly, and the other protocol have used other ways to approximate the peptide conformation. Okay, but what happens if we don't have these fragments? So what happens if we, in this fragment diagram, we don't have the fragments that will indicate that structure? Because as we know, the receptor has said, the receptor has a big influence on the context of this peptide. What do we do then? So,
perhaps close to the BC.
okay, so we have developed 2 protocols for this. The first one I won't have time to talk about today, but if you want to hear about it more, let me know. It was established in Biennial. A very talented student that is now moving on to a postdoc. So, Eisinger, Alisa Ramushi. What we did in this case, we said, okay, we are looking now at the interaction from the receptor side of view. So what does the receptor see when the peptide comes? And the idea here is that if this is really monomer complementation, we might be able to identify the peptide binding sites just by looking at the receptor surface and finding complementary regions in salt structures. So the idea is to look at where is okay, to basically look at this receptor surface. I'm going to show it here. We are splitting the surface into patches, and each of those patches, we are looking for the local motif of this patch within structures of the protein database, using a very fast matching algorithm developed by Gevorg and Victoria called MASTER. And then once we have found these templates, once we have found these templates here, we are basically extracting the fragment that fits in another structure together with what is bound to it in the other side. So basically we are copying the structure to the binding site together with what is located in the region that will be the binding site. And this can be taken as a starting fragment. So the idea is that we copy this green patch together with what is located next to it, which is green purple, and we use this as a starting conformation to refine the structure using FlexVector. And that works actually very, very well. And so this is again this performance flow that I showed you before. The important thing to remember here is that, first of all, it works better than this type of FlexVector protocol. And second of all, it's complementary, so not the same cases work. So now we are working on how to combine this, and especially it works for normal peptides. So while in this type of FlexVector protocol, we were really dependent on these fragments, so the normal peptides didn't work. In that case, we can actually really find very beautiful matches. And importantly, we find this both with interacting on interfaces and also within protein monomers. So, okay, so the third part, which I'm going to talk about in more detail, is using AlphaFold for peptide protein docking. Again, along the same lines, if it's really a monomer complementation, we can actually use it as an addition of the monomer. And so, what we have done in previous years, we thought about this monomer complementation by just using the sequence of the protein, adding a polyglycine lipid, and then the peptide. And if it's really a monomer that folds, we could basically fold the protein together with the peptide. And we tried to do this using protocols like Rosetta and Rosetta Fold, and it failed miserably. It really didn't work. And the reason why it didn't work is because the polyglycine was thought of something that we have to fold. They couldn't really identify these unstructured regions. Neither Rosetta Fold or Rosetta and other protocols that we tried. And other people have tried similar things and it didn't work. And so we were really desperate. But then the AlphaFold code was published. And as soon as the AlphaFold code was published, we immediately tried it with AlphaFold. And the reason that it is going to work with AlphaFold is because when you look at AlphaFold predictions, it's not only that AlphaFold can identify the structure very well and give you high confidence estimates for this, it also identifies surprisingly well unstructured regions, even better than IBSBC that has been developed very lots of work over the years. So the fact that AlphaFold can identify these unstructured regions was a very important finding for us, because in this case it means that we could actually use this protocol, and it really worked. So this is how our predictions look like. So we just added the polyglycine. This is a successful prediction. You can see here. Okay, I don't know how to do this. I'm pressing on this button, so you can see here this is successful. The unstructured region is shown as an unstructured region. We know that this is stuck, but the peptide is really modeled very well. And this case is a failure. In this case, we just have we failed, and we know it because the peptide just points out in space. So that was the original implementation of AlphaFold, not the multi-layer version. But, so what we did is we basically combined this method, which we tried it on a larger set. So what we show here is again similar plots for three different colors. So the first two are the dataset that we used before. The dataset that contains a couple of structures where we know the motif, a couple of structures where there is no motif known, and then a dataset that we put together with hard work about 100 interactions that all are non-relevant but equal, so they all involve a very different domain trying to peptide. And so what I'm showing here is how well AlphaFold predicts the structure of the receptor separately and the peptide. So in principle, the take-home message here is that in many of the cases, in large fraction of the cases, AlphaFold is able to identify the structure of the monomer and the structure of the peptide, which is maybe less surprising because monomers, this is what AlphaFold is trained on. But the important point here is what we are showing now. The important point is that it also works for docking. So what we can see here is for the RMS threshold. So what I want to show here is the performance, and again look at the cutoff. So you can see that within a cutoff of 2.5 angstroms, you can basically get most of the cases to work. So I hope you saw it. Again, this is not this is for the structure connected to a polydiesel linker. Later on, in the product fold, it was also possible to submit separate segments, and we combine both of them together, and they perform independently. So basically, in some cases, it works when we have the linker, and in some cases, it works when we don't have the linker. And we have separate chains. And what's important here to note is that this is done without any information about the multiple sequence aligned of the peptide. So when we use the regular alpha fold prediction, a multiple sequence alignment is generated, and in many cases we show that this multiple sequence alignment is really important for performance. In that case, we don't need it. So this is something to remember. The peptide doesn't have any multiple sequence information because it's very difficult to get significant hits. So it works, and that is actually something that allows us to learn about alpha fold performance using our protocol. One important thing is that we can model conformational changes. So what I'm showing here are structures of the bound and the anton conformation. And you can see that in these cases, the bound conformation is not available for docking. In general docking, it wouldn't be available and it would fail because in the bound structure there is some conformation, and there is some, in the unbound structure, there is a region in the protein that obscures this binding site. Alpha fold, since we fold and dock the peptide together, is able to solve this problem by folding both of them together and solving actually the problem. So we can recover structures that we couldn't model before. So that is really exciting. Moreover, when we look at the predictions, we can show that the regions that have a non-motif are very well predicted. And there is a strong correlation between the predicted accuracy, which is PLPT, and the RMSE. So cases where we have accurate prediction, residues that are well modeled are also the ones that are highly confident in predictions, and that is a possibility to identify new motifs and to identify the structures that are well modeled. So not only is it well performing, you can also identify when it works. And if we look at this in a larger scale, what I'm showing here is a plot that shows the RMSE of a model and the PLDPT. And we can see that if we take only the predictions that have a PLDPT value of over 0.7, which is what is usually done, we can get most of the models that are correct. And so this is really a very, very strong signal that AlphaFold is really well adapted for peptide docking. And for me, this is important because this actually substantiates our idea of how these interactions are occurring. This is really monomer complementation, and this should work. And the fact that it works shows us how these interactions are installed. And we also suggest something about the evolution of these interactions, how they have evolved to actually be possible. Okay. We can use these structures in a very similar way as we would use crystal structures by, for example, performing computation with alanine scanning. What I'm showing here is very simple, the correlation between what I would get from a prediction of the effect of a mutation to alanine from a model compared to what I'm getting for a predicted structure, from the crystal structure. And I can show that for the structures that have been modeled well, within 2.5 angstrom RMSE, which are in P, I get a very good correlation, and I can identify most of the hotspots. So that's really useful. So these structures are useful. Not only accurate, they're also useful. And that actually opens up the door for large-scale identifications of shopping and motifs and their interactions, and that's what we're working on now. So, okay. So I just want to say that this approach, since it works, it allows us to test also AlphaFold. And one of the things that we were interested in seeing is whether this is memorization or really learning. Because we could say, you know, these structures could have been in the database and AlphaFold knows everything from all the structures. But AlphaFold has been only trained on monomer structures. So it doesn't know about these interactions. But it could still be that there are fusion proteins that people solve as a monomer. And so we looked at all the structures that are built from fusion proteins, and we tested whether these are the templates that are used in our languages. And it turns out this is not the case. So this is not memorization. We really learn something that we can show. So our application here is one of the first to show that there has really been some deep learning and not only deep memorization, which is really exciting. It also makes a lot of errors. So as you might have seen, if you have taken on this AlphaFold, it doesn't really recognize post-transition modifications. So it will predict structures with the whole, because it has learned, for example, time to create different conformations, one with the phosphate and one without, and it doesn't really care. So we need to improve this. We need to basically look at what happens there, and there have been approaches we hear about them to see how we feed the models that AlphaFold generates. But this is really interesting because it shows that not everything what we learn is actually biophysics. We know that, but this is a little stage. Okay, so performance-wise, this is the performance of the three different protocols that we have developed. So you can see that AlphaFold and Touchman work pretty similarly. They work on different places. And last week when we presented this in another meeting, people asked us what we should use. So we should use AlphaFold because it's basically almost 100 times faster. But there are cases where Touchman and other protocols will be important, especially in cases where AlphaFold fails and we know when it fails. And also because our protocol that we developed previously is very, very important for, as a step for design, basically map the surface for possible design options, building blocks. Okay, so that's about it. I'm just saying so we can basically learn we can use these protocols that we developed to learn from deep learning, and we can use deep learning to improve our protocols. That's in short what I wanted to say. Okay, so thank you. So all the work fast needs to work, but sometimes we need to work fast. So this AlphaFold thing was done in 3 months. And it's really interesting to see because each and every of our protocol teaches us something else about peptide protein interactions. And we are working on extending this, on learning post-translational modifications, on improving and using transfer learning to actually do the end-to-end prediction specific for peptide protein interactions, including post-translational modifications. And I'm happy to answer questions.